again. As stated this morning, today we're going to discuss how we have put in work at Bouygues Telecom some real-time data integration using Apache Kafka and Apache Flink. For those who want to know a little more about me, today I'm a software engineer and solution architect at Bouygues Telecom. It's for 2 years now. On a normal day, I'll be playing with one of the tools, usually all the Hadoop ecosystem, including Hive, Impala, HDFS, and for sure Apache Flink and Apache Kafka, also some Elasticsearch. And if you don't see me coding, I'll be probably running. Actually, I did enjoy a little run in Tierkarten, if I'm saying this right. Today we'll follow the following outlines, just freshen up who we are, speak a little bit about Lux, the challenges we faced, etc., and the rest. So, as I said this morning, Bouygues Telecom is a full communication operator that provides mobile, fixed and TV and cloud services. We have more than 40 million clients and around 12 million mobile subscribers. We are pioneers in 4G, 4G++, ultra-high mobile data, that's 4G++ actually, and we have the first Android-based TV box. Some numbers, little numbers. The latest MPerf indicator shows that Bouygues Telecom is in the lead of the 4 operators in France, having the best global score on all technologies combined 2G, 3G, and 4G. It's the graph on the left. The graph on the right actually shows the 4G network population coverage. And as we see, we are really in a tight race with all the other operators, especially the orange one. So, having 14 million customers and all this concurrence, we needed actually to provide some quality service to our users to give them really a reason to stay for us. And that's what we do every day. So we try to improve our network and improve the services we are giving to our users. And to do that, we created Lux for logged user experience. The idea behind the system was to make use actually of the network equipment logs and provide quality of experience vision instead of a quality of service. That's a bit different. From a quality of service view, it's what the machines see. The machine can tell you, okay, there are some counters, all the counters are good, etc. But what we put in work actually is the quality of experience vision. Well, we can say if a communication of a user went good or not, if a specific user is suffering from some problems or stuff like that. And to do that, we had some other challenges is to keep the data moving in real time. So we had the real-time diagnostic feature to ensure 60-second latency end-to-end. Also, we have a business intelligence functionality that provides some KPI globally on what's happening on the network. We provide some real-time alarming and reporting. So, from a user's point of view, a simple communication depends only on the transceivers that we see here on the network. But actually what happens is a communication might traverse thousands of equipments, hundreds, even thousands, and errors could occur at any level. But luckily for us, every equipment on the network may generate some event logs that contains information about communication on the network globally. But there is a problem, not a problem, but a challenge to collect all the logs generated by the equipment and process them so to extract some added value. So the first challenge we faced was to collect the data and move it from the different equipment sites to somewhere, somewhere where we are going to process them. So the first challenge was data movement, and the second one was to process data. Okay, we have our data, we collected all the data on the network, but the data is all the time, not sometimes, but all the time raw. It doesn't contain any information actually on any user information or any business logic in it. So we got to transform it before making use of it. So the second challenge was to process data. So how we have some question how to transform it, how to make the results available as soon as possible, since we were looking to make a real-time system. So first, okay, we imagine the system, a classic Hadoop system, will be doing some Hadoop since we have all this volume of data. Okay, a classic system will be, okay, I have my data sources, I'll collect the data using any protocol, any usable protocol, some FTP, some Flume, some FSPut, and put all my data into what we call a raw data store on HDFS, okay? And then process this data using a succession of batches. So there is a batch job one that will produce some enriched data. We will call it version 1. And there is a batch 2 and so on to produce the latest version of data, name it enriched data VX, that will be later exposed to the users for diagnostics, etc. Also, data may be exported to external systems such as, I don't know, Elasticsearch or other external systems, Kafka or other stuff. So at every level, we can export our data to other systems. But the problem with this one is there is no real time. I don't know if you know anyone who actually put in work real-time solution using batch processing or micro-batch processing. So we said, okay, there is no real time. We have to look to another problem, to another solution. Sorry. And the thing is, the world moves fast, and data must move faster. Since today, big data has really changed. Data is generated, collected, and at predictable rates. So at Busy Hour, for example, we can have 10 times the volume of data we have in the morning. So. And all this data arrives fast, so there is really a need of a system that can move all this data really fast, including processing. We started from LinkedIn's design integration pattern, the one that says, okay, let's take all the organization data and put it all in one place. Okay, that's great, but the data is all the time raw, there is no information in it, so how could we process data and put it and make it available again, ensuring real time? So that was the second biggest question. The first, Apache Kafka actually answered our need to collect data and keep it moving in real time fashion. So all the sources that our data sources could send their data into Kafka, and the data is instantaneously available. So that resolved the first problem, the data collection in real time. But we still have our second problem, we say, or challenge, it's the data processing. So we had 3 choices actually. The first one was to process data at the data sources before pushing them into Kafka. But this solution didn't work for us since most of the times data sources have really limited resources. Their network equipment, they have some small CPUs used mainly for other functions, for telecom functions, and the data collection log actually will have only 1% CPU, let's say. So processing the data at the data source wasn't viable. Another point was that the solution is too hard to maintain. Imagine that tomorrow we're going to change our business logic, the way we are transforming data and processing it. We have to redeploy all the new business logic on all our equipment data, and that wasn't possible. It costs us too much. So the solution wasn't retained. We decided to push the data raw. Arriving to solution 2, that was, okay, our data is in a central repository in Kafka, it's raw data. We're just gonna tell our data subscriber or consumers that the data is raw and you have to process it before using it. But this also has some drawbacks because, okay, we have to implement all the business logic also on all the consumers, and also the same data is processed many times by the consumers to produce most of the times the same results. So there is a waste of resources here. So we decided to provide data in a usable format. We must provide it in a usable format. Arriving to the third solution, the one that we retained, and that was to process Kafka's raw data and push it back into Kafka in a more usable format. So the idea was, okay, we have some raw data in Kafka, let's process it in real time and push it back, feed it back into Kafka in real time. So our data subscribers and consumers will find data in usable format and make use of it. Okay, the benefits of the solutions are the following. The business logic will be implemented in only one place. So there is some source of truth, central source of truth actually. All the business logic is implemented in one place. Okay, so if the source of truth says it's this way, then it's this way. We don't have to compute other stuff later. So the other thing, it's resource efficient since data will be processed only once and consumed as many times as needed. All the processing side will be done on a single, in our case, cluster, so it's really resource efficient. And also, this solution gives the data subscriber more time to focus on their business logic, so they can implement and their business logic, the one they calculating indicators or other stuff. Finally, this solution enables simply to, if you have some new data sources or data subscriber, it simply subscribes to a Kafka topic and uses the data or writes into a Kafka topic. So the evolution, the handling of the solution is really simple. But the challenges are still the same, keep the data moving in real time. And to keep the data moving in real time, we needed a data processing pipeline, a very fast data processing pipeline. Kafka, it ensures data movement in a real-time fashion. So, but we had to process data in more faster way. Okay. The previous schema that we presented changed a little bit. So we still have our data sources. We have written up some collector, what we named a collector application, Kafka Producer. It's simply an application that knows how to write into a Kafka topic and spools some directories in data sources or stuff like that. So it just normalizes the way we collect data. Okay, it's a sort of connector to many data sources and pushes that data into Kafka. And instead of writing data directly on HDFS in raw format, we push it into what we named Kafka topic raw that will contain our raw data. This topic will be processed later using a streaming application to produce our enriched version of the data, V1, and push it into a Kafka topic V1 that will be also processed to produce other enriched versions of the data, and so on, to the last topic, Kafka topic VX. As we can see here, we can actually write data into the HDFS if needed at any level of the pipeline. It simply requires to do from Kafka topic 1 to HDFS. So, and we also can export our data to other systems, to system 1 to system X. So this solution helped us to keep the data moving in real time. But the biggest challenge was actually to find the right processing framework that supports real-time streaming and with low latency. So we can process our data and push it back into Kafka with latencies less than a second, actually milliseconds today. So, as we said, the challenge was to be fast, really fast. At the time we started working on the project, the tendency was Spark and Spark streaming. So we did a POC using Spark streaming that took us around 2 months to development. But unfortunately, our experience wasn't that good because we have just wasted some time trying to make micro batching work for our solution. So after trying to put the application in pre-production in tests, we have developed some libraries that helped us implement our business logic about enrichment and decoding our data. We have written a simple application that simply does, okay, from Kafka, that reads data from Kafka, that performs a simple map that maps every line of data into another one and push it back to Kafka. But actually it didn't work as expected, especially in busy hours. As I explained, in busy hours there is more data than usual. So our jobs kept failing out of memory all the time. On busy hours, the job kept failing out of memory. Also, there was some latency, more than a minute, since every job needed to be scheduled at least 5 minutes, each 5 minutes, so we can process all the data we have accumulated during the 5 minutes. So it didn't really help. Also, there were too many configuration parameters. For a simple application, okay, I don't know if you know Spark, they use what they call RDDs, and you had to specify a persistence level for each RDD, so to decide which RDD you keep in memory and which RDD you keep on disk. RDD is simply a presentation of a stream in memory, and this made the job development really difficult. Also, the version we tested, it was Spark 1.3.0. As I remember, used HDFS as a write-ahead log to ensure the fault tolerance. But actually, this is already handled by Apache Kafka. As we all know, in Apache Kafka there is a possibility to replay to replay your job and start at any level you want. So there is no need to write data into another external repository to replay your data. It's still on Kafka, so you can just restart your job and you start consuming where you left. So Spark didn't really work for us. But fortunately, as I said before this morning, I was at one of the meetups at Paris, and Robert gave an amazing talk about Flink, at what we can do with Flink. So at Week we call it just the elegant. Since the day we have seen the source codes of Flink and how simple they are, really, I invite you to read some code. It's really simple to understand. There is no magic behind it. It performs some magic stuff, but it's really simple in a way that makes it elegant. So at Flink, we love to call it Apache Flink the elegant. So that day, I have discovered, okay, a processing framework, an open source processing framework that can do all the stuff I was looking for. So it ensures true streaming, no microbatching, so there is no more latency. It handles back pressure nicely. There is an excellent blog post on Data Artisan explaining the back pressure handling mechanism of Flink. I invite you all to read it if you are interested in streaming mechanism. So it was fault tolerant, and it ensured high throughput, and it was scalable in addition of many other features. So we have adopted Flink. We were really one of the early adopters, I can say, of the Flink streaming feature, especially the Kafka one. So I have picked this slide from Stefan's presentation this morning that shows IoT mobile application use case of Flink with Kafka. And I just want to show you that we have exactly the same thing as Big Telecom. So it isn't just a theory or a design pattern that doesn't work. We have this pipeline working today in production at Big Telecom. So what we have is as many equipment as you can imagine, generating logs and collected by Apache Camel and push it back into what we call the heart of Flux, which is Flink plus Apache Kafka, before exposing data to external system as listed. Okay. I want to give you some, before diving more into Lux, I'm giving you some numbers. We have 4 billion event raw event a day. At the entrance of our Kafka cluster, we receive around 4 billion events a day. We have totally 26 Kafka topics, including 6 rows 1 and 20 enriched versions of the data, 6 main data types, around 100 data sources, and that totals 700 gigabytes a day, snappy compressed. All this runs on a CDH5 cluster, including 2 Kafka brokers, 20 data nodes, and around 750 terabytes of useful HDFS storage. So, the design pattern we presented, we're using globally Apache Flink or streaming framework with Kafka. We have put it in work actually in many use cases, and here I will try to give you more details on a specific use case, what we call mobile CDR use case, in which we still have our data sources that generates data every 5 minutes or 2 mega rolling files actually every 2 megabytes or 5 minutes. We collect this data, we push it into what we have called the CDR binary topic, the first one. So CDR binary actually it's data in a binary format. It's not human readable, it's really binary. It's as and one encoded data. This data is processed using a first application. The first application, what we call binary decoder. It simply takes the and one data decoded and put it back into CDR decoded, which is more human readable data. Next, the decoded format is processed using another app that uses Apache Flink in addition to Redis as a lookup live reference data to produce an enriched version of the data. The enriched version of the data differs from the initial data by containing additional informations calculated from the lookups. Next, the enriched data is processed again. Actually, it's just formatting, some formatting, so it's not really processing, it's just formatting. As you all know, Elasticsearch works well with JSON, but sometimes to make user queries more easy to write, you have to format your data in specific way. So we have written an application that simply formats the data and push it into a Kafka topic that will be later indexed in Elasticsearch. Also, the same topic, the same enriched topic is processed by another streaming application that uses a window of 15 minutes and computes some counters. In the example of the use case of CDR Mobile, it's actually the number of calls to emergency numbers like 911, for example. So it counts on a window of 15 minutes, the numbers that were destinated to 911 calls, and push the results into a live, what we called alarms, live counters topic that will be next pushed into Zabbix. Zabbix is an alarming system. So also note the same enriched data is pushed out to an external Kafka cluster of the company, the commercial IT department in this case, because also them have other use cases of the data, so we have to push the enriched data to them. They don't know how to process data, how to transform it from binary to enriched format, so we do that for them and push the result into an external Kafka cluster. Also, we write some data on HDFS for other reasons. For historical data, we have the binary format and the enriched one combined to reference data to produce some KPI views that are exposed to our users using Hive and Impala. Globally, we use Business Object U and Tableau software as presentation software. Well, all what I showed you actually was just a design. Those are the numbers. Later, just before we came here in Berlin, we just did a quick stress test. We took our biggest raw Kafka topic that contained around 2 billion events, the equivalent of 500 gigabytes compressed. The topic was on 10 Kafka partition, and we had started a job on using 10 Flink task managers with with only 1 gigabyte memory, and we have produced the 2 graphs. Actually, the topic contains the data of a whole day, so you can imagine it's the event log data of a whole day. So Flink was able to process it in less than an hour and a half, and then came back to the normal processing rate of the arrival of the data. Also, all the packets were processed in less than 200 milliseconds, and we haven't never dreamt about a system that would let us process data as fast. So this is only one of the use cases, just a note. Before we finish, I would like to cite some features that we really liked about when using Flink, actually. First was the development cost. It's true. First, once we started our streaming development project, we started using Spark. So we had our enrichment libraries, decoding libraries already for use. So the transition from Spark to Flink didn't cost us as much. Actually, it cost us around a week development. It was really quick. We had just to rewrite our Spark job into Flink, and it works directly. Also, putting other people to work with Flink was really easy because it didn't require any knowledge on how Flink does actually work internally. You just needed to know the APIs, what is exposed to user, how to use it, and it works. So putting other people to use Flink was really good, and it was really fast. Also, we really loved the ease of testing and development. Personally, I admire the local execution mode, so you can debug your code really fast before pushing it on a cluster or starting a cluster just for testing. Also, no out of memory. Since the day I started using Flink, I hadn't had any out of memory actually, so this is really great. And also efficient resource management and excellent performance even with limited resources, because even if you have the biggest cluster on earth, you will want to run other applications on your cluster, so you just need to use the minimum, and Flink knows how to run any application, I say, even with the minimum of resources. So and this is really great. Also, I would really want to thank my friends of Data Artisans. As I said, we were one of the early adopters of Flink streaming and Kafka, especially Kafka streaming, and we worked with them to provide the best connector ever for Kafka. So they helped us and they coded for us the best Kafka connector ever that supports true streaming, exactly once processing, ensuring low latency and high throughput. And also we have required some other features such as yarn features. I don't know if you're familiar with the yarn mode, such as yarn maximum failed containers that serves actually to define the number of retries after a container failure when your application runs. I'll give our example. Our application runs 24/7, so we don't want any external interaction with the application. So if the application fails, it should auto-repair and auto-restart with no external user interaction. And this feature helped us by putting maximum failed yarn containers to -1. You just tell your application to restart indefinitely, and so the application will run 24/7 with no user interaction. Also, the yarn detached mode, I don't know if you have known the first version of Flink, you had to keep a session open, actually console open, a bash open, so your application runs on Flink. But now there is the fire and forget mode, so you just launch your application on yarn saying in detached mode, and the application will run with no need to keep any terminal open. And this is also one of the nicest features we had. We have done great things using Flink on Linux, and we still have other things on the way. So the first one is to connect Linux to other data sources. So this is our heart of business. So it's local, and the other stuff are the following. We want to use the job manager high availability, so the applications, as Stefan stated this morning, to delete the single point of failure in the Flink jobs. We want to write our data on HDFS using the new file system file system sync. It's part of the O10 release, currently in development. Also index our data using the new Elasticsearch sync and do some Flink ML, and why not some contributions to the Flink project. Well, that was all for me. I don't know if you have any questions. I'll be happy to answer.
Hey, I was just wondering, do you do any stream joining on the data, or is it just more or less straight map tasks, or do you join different things on different streams in your jobs?
Different screens on different jobs, okay.
So you keep a local state or
the use case or the design pattern?
No, if you use it in your application.
If we used our application on other...
No, if you do any stream joining with Flink, like keeping a state on the mappers and the job.
Keeping the state on Flink?
Local state and stuff like that.
Actually, the application are more than maps, map jobs. It does a lot more. We do some grouping, we really produce not only an enriched version of the data, but a new data that is totally different of the first one. That's why we don't keep any state in the Flink application. I don't know if this answers your question because.
Yeah, I think so.
Thank you.
Hi. On one slide, you stated that you ingest your data into the Hadoop and use Hive and Hue and Tableau for exploration. How is the latency between ingesting the data and evaluation? I mean, is your business intelligence or your business department happy with the duration of this data processing until it can work on the data efficiently? Or
actually, there are some business needs that pushed us to choose this design, to write data on HDFS. So we can do some exploration later, maybe verify what we are doing is right, etc. That's why we do need to write historical data on HDFS.
And how fast is data available on that layer?
How fast? It's really fast to write data from HDFS.
No, I'm asking because we are facing a problem like this. We are ingesting data into Hadoop and would like to work on that. And business departments are constantly asking for more accurate and more update data.
It depends on the storage format, I guess. So and the way you write data. So we do write data in using Apache Flink today. And we just dispatch it into folders actually, so we don't, it depends on the compression algorithm, but it's really fast. We can write our data in less than 5 minutes, I guess. So.
How long do you keep the events in Kafka for, and how do you manage backups?
How we keep Kafka? Sorry,
how long do you keep the events in Kafka for?
How long we keep data into Kafka?
Yeah.
Actually, it depends on the version of the data. So there are, as we saw, there are many versions of the data, and the size of the data depends on the data itself. So there are normally one topic 24 hours or around I don't know 700 gigabytes. So we have defined a rolling window of 1 day globally on all the topics. And if the topic is consumed for using another external system, it's usually 2 to 3 days of data.
Thanks.
Yeah, welcome.
You mentioned that you use CDRs. Are you planning to use other sources from the mobile phone network, like cell trace from the radio network or things like that?
Other data sources from the network. Actually, it depends on our engineers' needs. So if they need external data, we'll integrate it into Lux, so into the system. If they don't need it, we will not. So.
Okay.
It's not to us to decide. We don't do the data science. We are a solution. We develop solution. So there is another job that is a data scientist who decides which data they need and how they need it. We just put the data in work for them. So.
Thanks. Okay.
One challenge when you need to integrate in real-time network equipment is to have a trade-off between the granularity of the event window, for instance, each minute, each 5 minutes, and still guaranteeing the SLA of the equipment. So, I mean, not impacting the performance of the equipment. So how do you manage this integration of allowing to push in real time and in the same time guaranteeing the SLA of the equipment?
By real time, end-to-end real time 60-second latency, we meant the moment the event logs are available on the equipment side, and the moment the data is available to the user. So if the equipment doesn't support real-time event log generation, the data will not be available for the users in real time according to event generation timestamp. But if the equipment supports that, so there is no problem. And today, most of our equipment supports that, so we don't have such problem on our side. So we are able to collect the event logs normally on the equipment side.
Yeah, similar is giving a thank you to Michael from ResearchGate for basically being an early adopter of the Batch API. I think the team from Bouygues was really an absolute early adopter of the streaming API. I think they were putting the first job into pre-production before the first version of the streaming API was released, which was quite impressive. Yeah. And they helped us figure out quite a few things, like as simple things as how do people interact actually with a yarn cluster and streaming. It's different than in Batch, and we didn't realize that. They basically helped us figure out the interaction patterns. Or things as simple as when Flink consumes from a Kafka cluster, how does it need to expose the progress it makes for other tools to pick it up and monitor it? All these things like that. They didn't really work out in the first version, and they came back to us a lot of times and say, this actually needs to work, and this and this is the way people interact, not like this. So they helped us quite a bit in getting these things, I think, right.
We're really happy to work with you, so thanks again.